Welcome to Science with Steph, the show where I think way too much about the world around us and then share the best bits with you guys. This week I'm going to Vienna. I'm going for a holiday, I'm going for my birthday, but I'm going to film a bit of my time there, compile some of the best bits together and share some of the scientific concepts that some Viennese physicists have come up with, and hopefully we'll have a good time. It's not that far away from the UK, about 2 hours on a plane. Luckily you don't need to join me for the whole 2 hours. By the magic of YouTube, you can join me practically instantly. Okay, I'm gonna go to Vienna. We have finally arrived after hours of delays. I'm going to give you a little tour of the flat because it is lovely. So this is a little bit of the hallway. Look. Aww. Posh bathroom. And this is the living room. John in his paint me like one of your French girls pose.
It's true. I do want painted.
Hiya John.
How was that?
It's my birthday today.
It's our birthday today.
What are we doing today?
We're going to go to Boltzmann grave.
Yeah.
Check out some Entropy.
Yeah.
Hopefully followed by the cat cafe.
Cat.
And then maybe some longboarding if we have some time in the evening, right?
Well, you can longboard, I can...
Oh, you're going to inline skate, yeah.
Roller skate. Yay! Okay. So we are here at a very important physicist's grave. This is Ludwig Boltzmann, who was an Austrian physicist from about 100 years ago. He studied here in Vienna and made some massive contributions to physics and equations. He was very much ahead of his time because he was one of the only physicists around that time to believe that atoms existed, and a lot of his research and studies was around the concept of atoms, particles making up all matter. And actually he did a lot of work with a Scottish physicist called Maxwell, who also believed in atoms, and so there's that Austrian-Scottish link which I like. And one of his most important concepts or most important relations that he proposed was the equation of entropy, which is actually etched on his grave. So I don't really know anything about entropy. John, would you like to explain it to me?
Yeah, so Boltzmann's contribution to modern physics can't even really be understated. The idea of entropy, it essentially runs the universe. So entropy is a description of the different types of orientations and the different ways we can set up atoms in the system. This is actually shown in the equation here. So the equation goes S being entropy equals a constant K logarithm of the number of microstates. What these microstates are the different ways we can set up the atoms. So let's take an example for a glass of water versus an ice cube. How does entropy differ between these two things? Let's start with the cube of ice. We all know that ice is solid, nothing really moves around. That means that the amount of microstates you can have, aka the amount of places we can put those atoms, is very limited, giving us a very low entropy. But you probably know from the second law of thermodynamics, entropy increases over time, because we know that as things move in equilibrium, entropy goes to a maximum. So as ice melts, as we know it does, the atoms will start to have lots of different places they can go, lots of different orientation, lots of different positions, aka a higher W giving us a higher entropy. That's why we say entropy always increases.
That's a really good way of describing entropy actually, John. I really like that. And the good thing about this equation is that Boltzmann knew that there was a relation between entropy and the number of states that something can have, and he knew that it was going to be a log law. But this K constant is actually called the Boltzmann constant. You know you've made it as a proper physicist, right, if you have a constant named after you. So Boltzmann not only has a constant named after him, but he has multiple physical things named after him. So what other things are they named after?
Well, the Boltzmann Constant, it seems to appear in all ranges of science, from the really small quantum mechanics, statistical mechanics stage, right up to like the cosmological stage. You get things like Wien's law, for example.
Yeah, Wien's law. It comes in the black body radiation, which describes how much the sun shines onto our Earth.
Various probability, the Boltzmann probability distribution.
Yes, you've got Maxwell-Boltzmann distribution, which is where particles are going to be. You've got the Boltzmann Constant as well, which is really used in astronomy lots. What else?
I can't think of anything else off the top of my head.
Boltzmann is
and of course the entropy equation.
And yeah, that's what people call the Boltzmann equation as well, which is a really important physical equation. So really, really famous physicist here, really special to be visiting his grave, and we shall show you some examples of entropy next up. So we spoke a bit about entropy while we were visiting Boltzmann's grave, and now that's a really hard topic to discuss. Not many people fully understand what entropy is. In fact, I'm not going to sit here and pretend I really, really deeply understand what entropy is, but it's a way of describing a system that can have lots of different ways of configurations. And a good example is a pack of cards. Now you could say that one configuration or one way that the cards can be set up is completely in order. You know, ace of spades up to king of spades, ace of diamonds up to king of diamonds, etc, etc. And then if I was to shuffle the cards, then that's going to increase the entropy, or it's going to increase the number of different ways that these cards can be set up. And look, I'm not very good at shuffling because I've already managed to like mix things up. That's not very good. World's worst magician. And you know, what you could say is that all these cards laid out all over the table is a very chaotic state, because all the different cards could be in a different configuration. But a very, very controlled state is something like a stack of cards. If I was to put these cards into a very neat stack, then what you're doing is telling the cards to be in one very, very controlled state. And what you're doing is, when you're adding more particles or cards to the house, what you're doing is increasing the energy in there, but also increasing its chances of collapsing. And what entropy does, it wants the cards to collapse into the more chaotic state, which is the higher entropy. So all collisions, all transfers of energy, every action increases in entropy. And so a lot of physicists say that entropy is our arrow of time, because entropy dictates that, I'm not very good at this, entropy dictates that instead of these cards magically collapsing into a more controlled state, they're actually going to collapse into a more chaotic state like that. I'm not going to complete the 3-tier of cards because I've done this take 100 times over and I can't complete the stack of cards. I'm done. So I hope you enjoyed this episode of Science with Steph. It was a bit different this week because I was on holiday and I was vlogging, but if you did enjoy it, please give it a big thumbs up. And my question for you this week is, if you had the power to name a physical constant, what would you call it and why? If I could name a constant, it would be cats, because I'd be like, here's exactly 2.7 cats, please. Oh no, they don't like me anymore. I bring out new videos every Friday, so if you want to watch my last episode, you can click here, or if you want to watch a video that the YouTube algorithm thinks that you'll enjoy best, you can click here. Anyway, that's all for this week, and I'll see you next Friday. Bye!